Welcome to the 53rd lecture in this series. So in this lecture, we'll continue with our discussion of alternating forms or alternating tensors. And so let me complete the example that I had begun with last time. The second example was consisted of starting with a basis omega 1 up to omega n, which I took to be the dual basis of the standard basis of Rn. This is the basis of a basis for one forms, for the space of one forms, namely the dual space of Rn. And by definition, omega I Ej is 1 and so on. What I wanted to claim was that if I take the iterated wedge product starting with omega 1, then omega wedge, omega 2, etc., all the way up to omega n, I just get the determinant form on Rn. And notice that I have to be careful about putting brackets here when taking wedge product of multiple forms, because as of now we don't know that this operation of wedge product is associative. But soon we'll prove that it is, and I won't have to bother about putting brackets. Well, so in order to prove that this is the determinant, omega 1 wedge, omega 2, etc., first we made a general observation that if we have an n-dimensional vector space, then the space of n forms has dimension 1. So in other words, any two n forms are just multiples of each other, scalar multiples of each other. And having proved this, we know that the determinant is already, this thing here is already an n form, and the left hand side alpha is also an n form, since it's a wedge product of one forms. And so both are n forms, and this general observation allows us to conclude that alpha is c times beta for any two n forms. So therefore, the wedge product, the iterated wedge product, is some constant times the determinant. So applying this general observation to this specific case. Now what we want to say is that the c is 1, this constant is 1, then we would be done. So we just to see that c is 1, just evaluate both sides on the standard basis E1 up to En. And if we do that, the right hand side, the determinant of evaluated on E1 up to En is, we already know it is 1, where the EIs are written as column vectors. Now we are in the process of checking that the left hand side is 1 as well. So I want to say that this iterated wedge product evaluated on this is 1. So, and it's an inductive process. So let me call the first n-1 wedge products as beta n-1. The whole thing we can write. And then we just wrote this as beta n-1 wedge omega n, and then use the definition of the wedge product to write it like this. Now the last, instead of going to the last step directly here, what I'll do is just notice that this, whatever I have here, is by definition alt, since beta n-1 is an n-1 form, in particular it's an n-1 tensor, so this is alt beta n-1 evaluated on E1 up to En-1. So, and since beta n-1 is already an alternating form, again it's a wedge product of various one forms, So this is just the same as we have seen that the alt operation does not change the tensor if it's already alternating. So we started with this beta n E1 up to En. Beta n is the full wedge product with the same notation. This entire thing, well, this entire thing here is beta n. So we started with that, and we see that this is equivalent, this is equal to this, and one can continue this process. At this stage, you can again write beta n minus 1 as beta n minus 2 times omega wedge omega n minus 1 and so on. Finally, you end up with beta 1 of E1, which is omega 1 of E1, which is 1. So therefore, the left hand side is also 1, and therefore the constant C equal to 1, since det E1 En is determinant of the identity matrix. Equal to 1. Right hand side is, yeah. All right. Now, I would like to, so this particular n form, which consisted of a wedge product of 1 forms, where the 1 forms form a dual basis. This way of constructing forms, I would like to generalize to any k form and prove various things. So what I want to prove, so this will take a couple of lectures. So I want to prove, first of all, some general properties of the wedge product operation. So proposition. First thing is that this wedge product operation is bilinear. So if omega 1, omega 2 belong to AKV and eta belongs to ARV, and you have two real numbers A and B, then A omega 1 plus B omega 2 wedge eta equal to A omega 1 wedge eta plus B times omega 2 wedge eta. So this is linearity in the first slot. Similarly, one has the same thing in the second slot as well. Eta wedge A omega 1 plus B omega 2 equal to eta wedge omega 1 plus B eta wedge omega 2. So it can be summarized by saying wedge the wedge product operation is a bilinear operation. The second thing is, now this is the part which is requires some work. The wedge product operation is associative. So here eta is anything else, some other, I've already used K and R, let me call it P. the point is that there are no restriction on the degrees of the forms. U1 has associativity, and the third thing is also very important, which is called anti-commutativity. So if omega wedge eta equal to -1 to the power kr eta wedge omega, the wedge product is, I'll put it within quotation marks, anti-commutative. So the reason I've used quotation marks here is that we don't always get a minus sign on the right hand side. It depends on the degrees. For instance, if K and R are even, say you start with the wedge, for example, if you start with the wedge product of two forms, both omega and eta are two forms, then omega wedge eta will be equal to eta wedge omega. One doesn't get a negative sign. So the fact that this power depends on the degrees is sometimes called anti-commutativity. Somewhat this is not the usual anti-commutativity. It's in this sense. Right. So these are the three properties that we are going to prove. Now of these three, the first is immediate from the definition. It is 2 and 3 which require some work, especially 2. I would like to prove this, and so to do this, I'm going to introduce certain K forms, specific K forms, and they will also help us obtain a basis of the space of K forms. And the way these forms are defined is exactly like the way we define the determinant in terms of these one forms. So I took iterated wedge products. Now, however, I'm not going to define. So what one has in mind is this: one wants to use this iterated wedge products, but instead of going all the way to n, I would like to stop at some k. And then, so in other words, take the iterated wedge product of k1 forms is what I would like to do. However, because of since we don't know that this operation is associative, it's somewhat inconvenient to work with this wedge products directly. So instead, we'll work with determinants, since we, at least in the case k equals n, we know that this iterated wedge product is actually the determinant. So even when k is strictly less than n, one can get something involving the determinant, which is what we'll work with. So let's start the proof. Along the way, as I said, we'll also obtain a basis for the space of K forms. So here's the first definition. Let I1 be a number less than or equal to all these I1, I2, they're all Ik less than or equal to. So I fix k less than or equal to n, and look at some numbers in between 1 and n. The multi-index I is an ordered k tuple. I equals I1 all the way up to Ik. Now if sigma is a permutation, on k letters, then we define I sigma to be, I just permute this I1, I sigma 1, etc., I sigma k. So I can do this. So essentially this I sigma in terms of if I forget the ordering, if I look at it as a set of numbers lying between 1 and n, it is the same as I. It is just that the ordering may change depending on the permutation. And we had done a similar thing on when we were dealing with k forms. We could let a permutation act on a k form and then obtain a new k form. Here we are just dealing with index sets. So, and as in the case of permutations acting on k forms, here too we then have, if I have a product of two permutations, it turns out to be the same as, you can first do I sigma and then whatever k tuple you get, on that you do tau. And this is quite trivial just from the definition for all sigma tau in Sk. This condition is what is technically called, is one part of what makes a group action. So this group Sk acts on the set of all I sigmas, and what one means by act is, one property is this. The other one is just that the identity permutation just doesn't leave the I sigma equal to I if sigma is the identity permutation. These two properties make up a group action. Right, so this is this. Now the other thing is, so this is the first definition. Now let's start with the vectors. Let omega 1, omega n be a basis for V star, the dual space. Define, this is the analog of that iterated wedge product that I was talking about earlier. Define for each multi-index I, I'm going to define epsilon I a k form by epsilon I acting on V1 up to Vk to be the determinant of the following matrix. Omega I1 V1, omega Ik V1, omega I, again I1, omega I1, yeah, it's Vk, omega Ik Vk. Where so this multi-index, as usual, the multi-index is I1 Ik. So I define it like this. The point is that the right hand side is a square matrix, so I can take the determinant and more. All these are just numbers. Omega i's are one forms, so they act on vectors V1 up to Vk, so I just get numbers. So for all V1 up to Vk in V. Right. So and after a while we'll prove that this is actually just the iterated wedge product of omega I1 wedge, omega I1 wedge, omega I2, etc. all the way up to omega ik will turn out to be the same thing as the right hand side. So, and also let's notice one thing, if E1, E2, En is the dual basis, is the basis of V dual to omega 1, omega n. In other words, as usual, omega I Ej should be equal to 1 if I equal to j, otherwise it should be 0. So, if it's the basis of V, then this epsilon I acting on V1 up to Vk is nothing but determinant of V1 I1 V1 Ik Vk I1 Vk Ik, where V1, I've expanded V1. If I expand V1 in terms of this basis that I had, I would write it as V1 1 E1 plus V1 n En, etc. Vn equal to Vn1 E1 plus Vnn En. Right. So these this is if this, so the statement that this equal to this is immediate because omega I1 V1, for instance, if I do omega I1 omega I1 V1 is the same as V11 omega I1 of E1 plus V1n omega In of En. So I'll write it as an example. So this is right. So this is, well, the only term which will survive is when this EI1 is the term which will survive. So and then I'll get omega VI1 and then 1. All the other things will be 0 because we are working with bases which are dual to each other. So the first term becomes VI1 and so on. Okay, so for example, another example of this construction is, this is not quite an example, I just did one specific index. Let's, using standard basis for R3 and R3 dual, we have E13. So this would be a 2 form. The index, this k here is called the length of the index, is equal to length of I, multi-index. How many entries there are? So here the length is 2 and so it would be a 2 form. So acting on VW. Well, according to what we have here, it's determinant of, and I'm working with standard basis. So if I expand V in terms of, so V is V1 E1 plus V2 E2 plus V3 E3, W is W1 E1 W2 E2 plus W3 E3. Then I would be, the first column will be V1 V2, and here it would be W1 W2, which is V1 W2 minus W1 V2. So this would be my two form, 1-2 form that I obtain this way. There are others as well, of course. I just took this index, multi-index 1, 3. And if I look at E1, 2, 3, which is a n form, which is a 3 form on R3, we know that we have already know that anything in the top dimension, any two n forms are multiples of each other. So in particular, E1, 2, 3 would be evaluated on, we would expect it to be just a multiple of the determinant of the matrix formed by V, W and X. It's actually the way we have defined it, it is in fact the determinant itself. So determinant of V1, V2, V3, W1, W2, W3, X1, X2, X3, which we write it as VWX. This is, there's nothing to prove here, just the definition we have stated. So far we have not even brought wedge products into play. So in fact all this, whatever I am doing now, could be defined even before we introduce wedge product. So that's one definition, and the other definition is, so this is definition 2. Let's introduce one more notation. 3. Let Ij be multi-indices of length k. Define delta Ij equals determinant of delta I1 J1 delta Ik J1 delta I1 Jk delta Ik Jk, where this is called the Dirac delta function. So this is, this is called the Kronecker delta, which is where delta Ij equal to 1 if I equal to j, is equal to 0 if I not equal to j. Is the Kronecker delta. Kronecker delta symbol. Just a notational device which keeps track of whether two indices are the same or not. Here the difference is, of course, this small delta Ij, where I and j are numbers, is something which we might have seen before, but the left hand side here, something which has to be defined, because it's these are multi-indices now, capital I and capital J. And that I defined to be the determinant of this matrix. Notice that every entry in this matrix is either 0 or 1. And in fact, the claim is that then note that one can say exactly what its value is, this multi-index delta, this is just the sign of sigma if neither I nor j have repeated indices and I and j equals I sigma, and is equal to 0 if I or j has a repeated index or if j is not a permutation, not, so here I should underline not a permutation of I. In other words, j is not equal to I sigma for any sigma. So let me write this clearly. So here j. And how does one see this? Well, that's a couple of ways. One is just use the fact that just use the definition of a determinant. That way one can see it directly. Or the other way is write a permutation as a product of transpositions, and then one can see this stuff, this thing here as well. Okay, so we'll continue with this next time. So let's stop here.